Hello, everyone. I'm Subhojoy, and this is something that is interesting. We are going to have this introductory sort of course in topology, and which I'm sure a lot of you are interested in. Let me start with myself. I'm Subhojoy. I'm currently in Bangalore. I'm an assistant professor in IISc. And I work in geometry and topology, and this is something I do my research in. And I've taught topology many times in different countries, in fact. But this is the first time I'm doing it online. So, and it's not going to be a traditional, sort of course that is in a classroom because of all the difficulties of this video and so it is mostly a reading course. So you'll have to sort of read up on the topics that I'll be discussing, and I'm there to supplement it in some ways, and maybe some whet your appetite in some sense. Okay, so let me start. So I wasn't sure what this audience was going to be, so I've kept it very light at the beginning. Right, but hopefully it will be of interest to you. So let me start with some sort of very basic stuff. Okay, so sort of going back to the beginnings of topology. Okay, so this was a few hundred years ago. So so initially it might seem it's I'll be talking about something which is different from topology. So namely, I'll be talking about graphs. Right. So suppose you take a graph. Okay, so and this for us is something which has vertices and edges, right? So there's some number of, let's say you have some collection of vertices, and then you have some edges between them. So that's what a graph is, right? So maybe it looks something like this. Maybe there are sort of two edges between vertices. We can allow that. Maybe there's some edge from a vertex to itself. We can allow that. So that's a graph, but then we also want it to be connected. Okay, so it's connected, and I suppose you can all guess what it means. So something which is not connected would be, so let me just. The not connected would be if you have, something like sort of this, right? So that's not a connected graph, but this one is, right? So this one, the one that I drew is. If I delete, so maybe if I delete an edge which is here, so then it becomes disconnected, right? But if we add this edge, then it's a connected graph. So that's what a connected graph is. And suppose it's also, I want something that is planar. Okay, so it's going to be, let me put it this way, write it this way. It's going to be also embedded in the plane. Okay, so and by this I mean that no edges cross. Okay, so something which is not embedded is, well, if I look at the same kind of graph that I was looking at, so suppose I have this and that. Okay, so that's, the edges are crossing, so we don't want that. Okay, so this particular graph, you can embed it, right? So if you just, instead of making it cross, if you take one of these edges and go around the other way, then that's the same graph, so it connects the same, it has the same edges between vertices, etc. But now this time it is embedded. Okay, so suppose I start with such a sort of connected graph embedded in the plane. You take such a graph. So something that happens. So let me just write. Take any such graph, something that happens is this graph will divide the plane into regions, right? So here, so these three edges here enclose a region R1, and then there's an R2, there's an R3, and the region outside, we say, is the fourth region, R4. Okay, so so that's also counted. So that the outside region is counted, and then so the theorem, this observation from a long time ago, is that if you count the number of edges, okay, so first count the number of vertices, then subtract the number of edges, and then you add the number of faces. Okay, so let me use orange here. That always equals 2. Okay, so no matter what connected graph embedded on the plane you take. Okay, and this is a theorem. Does someone know whose theorem it is? I mean, who first observed this? So this was by, this is Euler. This formula is called Euler's Formula. I mean, Euler had several formulas to that. Okay, so so this was shown by, approved by Euler, 1707 to 1783. I looked up Wikipedia. All right, and this is kind of it's a nice thing to, you know, tell non-mathematical people. Okay, so if you try it, you know, with someone who's maybe a kid, or, you know, someone else who's not into mathematics, you say that, okay, draw a graph and you put vertices and put edges and you count them, and it's always turns out to be so. So for example, here, let's actually, so we haven't tried it with this guy. So here the number of vertices is what? So let's call it V to be short. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 is the number of edges. Is a number of edges is let's see, it's 1, 2, 3, 4, 5, 6, 7, 8, right? So you have, oops, there's the wrong color. So that's 8, and the number of faces is well, so these are the number of regions rather. So I'm calling it regions. I'll talk about why I said faces a little bit later. So number of regions R is equal to 4. I've already numbered them, right? And then so you see that 6 minus 8 plus 4 is equal to 2, right? So so let me go over the proof very quickly, right? So this is something that there are a variety of proofs of this, okay? By the way, this was also, Euler was also credited not only with this beginning of topology. I'll say how this is related to topology, but this is also, you know, he's also credited with beginning graph theory, okay? And this sort of kind of the beginnings of the subject. And so this is kind of a basic theorem. There are plenty of proofs, and some of them are quite elegant. I'll give you some books to look at the very end. But there's a standard sort of the first instinct proof, which is this theorem, is to go by induction, right? So let me first do a special case though. So let me, so I'll talk about the proof by induction, but there's a special case that one starts off with, okay? So the special case is the following. So the special case is when so when there is only one region, so the connected graph determines defines only one region, which is outside, right? And so what's an example of something like that? So well, if you have some bunch of vertices, so you have a graph like this. Okay, so suppose you have maybe this, maybe that. So that's an example of a graph. There's only one region, right? So this outside region, this R1, let's call it R1, right? So by the way, can someone tell me what such graphs are called?
Is it something related to roads? Because Euler solved that bridge problem.
Yeah, that's right. That's another famous sort of problem that Euler solved. That's right. That's true. But this I'm talking about is a kind of a class of connected graphs.
The trees? Is it
Yes, that's right. It is exactly. That's exactly right. So these are called trees, right? So this is a tree, right? Because I mean, I've drawn it suggestively. It sort of has that kind of branching feature. And there's one feature of a tree. So a tree is some graph which has no cycle, right? So cycle is, so let me draw a cycle in the original. Let me highlight it, and maybe in yellow if it is visible. So this is a cycle, okay, right? And that's a cycle, and so on, right? So these are cycles are sort of closed loops, made up of edges, right? So a tree doesn't have any cycles. That's another way of defining what a tree is, okay? And for a tree, it's kind of easy for you to sort of check that the number of vertices, let me draw it in, because the number of vertices minus the number of edges, okay, is always equal to 1. Okay, so what happens when you try to sort of make a tree bigger, for example? You have to add, so you would take an existing vertex and you have to put in an edge and you put in a vertex, right? So that's what you do. So whenever you put in an increase an edge, you have to put in a vertex, right? So I mean, I'll leave it to you to sort of see how number of vertices minus number of edges of a tree is always equal to 1. So this means that this sort of Euler's formula holds, right? So holds is always true for a tree, holds for a tree. So this is the Euler's formula that maybe I'll kind of box it to something. Okay. All right. So this is so it's true for trees. So how do we do it in general? So this sort of in general, as I said, it's a sort of the proof by induction. Okay. So in general, you sort of prove by induction on, let's say, the number of edges. Okay, you can do it, with number of vertices and the number of faces, perhaps. So you can, there are a variety of ways you can prove this. So I'll do it by number of edges. Okay, and how does the proof go? Well, so the base case for your induction is when the number of edges is 0. Okay, so when that happens, then the graph, what's the graph? So the graph, it has to be a connected graph, right, with 0 edges. So then it's just a single vertex, okay? And so Euler's formula trivially holds, right? So the Euler's formula just gives you 1 minus 0, so 1 vertex, 0 edges, and 1 region, which is the sort of the outside, right here. That's the region, and that's 2. Okay, so the base case is satisfied, and then there's the inductive hypothesis. So assume that Euler's formula holds for a connected graph with, let's say, capital N edges. Okay, and so that's your inductive hypothesis. So let's prove it for n plus 1, right? So then if you take a connected graph with n plus 1 edges, okay, so if it is a tree, then there's nothing to do, right? You're done, because you already noticed that, it's always true for a tree. So then we are done. If not, So what does that mean? That means that somewhere in the graph, there is a cycle, right? Maybe let me draw a bigger cycle. Maybe there's a sort of a bunch of edges, okay, sort of all connected up and closing up, right? And there is a lot, the rest of the graph is doing something which I'm not drawing. So that's the cycle. I was drawing it in yellow, right? So it's marking. So that's a cycle. So what you do is, so there is a cycle, there's some cycle. There could be plenty of cycles where you take an edge belonging to a cycle and delete it. Okay, so let me write, so delete an edge belonging to some cycle. Okay, so any edge in the cycle. So in this case, maybe let's take this edge, right? And you can, so you delete it, right? So what happens when you delete this edge? Okay, so let's observe a few things. So first of all, so when you delete, so let me just write it like this. So then what happens is, number one, the number of edges decreases by 1, right? So you want to apply the inductive hypothesis after all. So let me write it in green. So the number of edges decreases by 1. You've deleted an edge. Okay, so the second thing that happens is, so the second thing to notice is that the graph, the new graph, is still connected. Why is that? Well, it's because you took some edge from a cycle, right? So now if there is a cycle, right, and so then if you delete an edge of a cycle, well, you might worry that now you've disconnected it because you can't now go from this vertex to that vertex along that edge that you've deleted. But since it's a cycle, you can go the other way around, right? So you can go the other way around, and it's easy to check that now. So this new thing is still connected. Okay, so these are two observations. The third thing that you observe is that what happens to the number of regions. So earlier, when you had that cycle, let me draw it again, right? So you had the cycle, you have that edge inside there that you deleted. You had a region that the cycle enclosed, right? You had this region, let's call it R1. And there was a region which was maybe on the other side of that edge that you deleted, right? So let's call that edge, that edge orange like we were doing. But when you delete that, right? So then when you delete this edge, then R1 and R2 merge, right? And become one region. So the number of regions, let's call denoted by orange, the number of regions decreases by 1. Okay, all right. So now what happens? Well, so 1 and 2. So let me. So say if you look at 1 and 2, 1 and 2 means that in the new graph, the inductive hypothesis holds, right? So the Eulers formula is true because you get a connected graph with n edges. So you know that Eulers formula is true for the new graph. And if you look at 1 and 3, right? So this tells you that if Euler's formula is true for the new graph, it's also true for the original graph, right? Because to get from the new graph to the original graph, the number of vertices remains the same. Number of edges goes up by 1 and regions goes up by 1. So if you look at V minus E plus R, then that remains the same. So then this implies that Euler's formula is true for the original graph. Okay, so this is a sort of a simple enough theorem. So this completes the induction, right? So this is a simple enough proof, right? So you just sort of this is one of those proofs where you follow your nose, Okay, so you have an idea that, okay, maybe it can be done by induction, and then you just follow your nose, you'll come up with this proof. There are nice proofs without induction. Okay, so I'll give you references. So there are sort of very elegant proofs using a little bit more graph theory.